Good evening, everyone. I hope you had a wonderful day today. Right, today we want to finalize our topic on chems. Remember, the chems is part of the big family of loci. So we want to finalize the topic on chems, but we are still looking at simple harmonic motion as well as uniform acceleration and retardation. Still looking at the roller follower, but today is basically about revision exercise. So I'm not going to talk much with regards to this. I just want us to go straight to what we are supposed to be doing in terms of recapping and panel beating each and every aspect that we touched during the course of the week, this week and last week. Right, so it's a revision task. We are going to look at question 2 of November 2019. So we are going to look at the construction and application of the whole concept of loci and in particular chems. I want you to enjoy the lesson and all the best. Remember, in doing so, you need to make sure that you are able to see and be sure that you'll be able to remember all the aspects of the topics or tasks that we are doing. But in doing so, you are supposed to be practical. Get a piece of paper, get your drawing board, get your pencil, and sit down and draw. Enjoy. Thank you. Right, okay. Like I said, we are going to look at a past exam paper, and this one is for last year. That's question number 2. It's loci, it's the chem. The detail of a wedge-shaped follower and the camshaft, the position of center point S on the drawing sheet. Right, the specifications are as follows. The follower reciprocates on the vertical center line of the camshaft. The minimum distance from the follower to the center of the camshaft is 17 millimeters. We shall look at that. Right, rotation, it's anti-clockwise. The cam imparts the following motion to the follower. It descends 56 millimeters with uniform acceleration and retardation over the first 180 degrees. Right. If we look at our diagram, let me just focus on that. There you go. This is our diagram. Right, we have got here, that's our camshaft. Then we have got the follower in position, in its starting position. And we are also given that the minimum distance from the center of the camshaft or the cam itself to that point is 17 millimeters, okay? Right, what we talked about earlier on is that when we are talking about falling, right? Falling, it's going towards the camshaft center, but in this case, because this is at the bottom, we find that the falling, which is the descending, right, it's going downwards like that, which is moving away from the camshaft center. Right, so it descends 56 millimeters with uniform acceleration and retardation over the first 180 degrees. It rises 20 millimeters with uniform motion over the next 45 degrees. There is a dwell period for the next 45 degrees. It returns to its original position with simple harmonic motion over the rest of the rotation. Draw to scale 1:1 the given camshaft and the wedge-shaped follower at the minimum distance. So the given camshaft and the wedge-shaped follower at the minimum distance. Remember the minimum distance, we said that the distance from this point to that point, it is 17 millimeters. Right, so let's factor this in, right, in terms of our diagram. So I can draw a faint line like that. Sorry about these two lines. They are not part of our drawing. So something like that. Right. Then the camshaft diameter is diameter 14. So you measure radius 7, mark 7 like this. Take your canvas. All right. There you go. Right, so that is our camshaft sender, right, which is accommodating the camshaft itself. Right, then once we have done that, you take there you go. Right. So the camshaft is now in position, right? So that's the camshaft. We have defined the camshaft. Let's also measure the minimum diameter, right? Which is the minimum distance from the camshaft to the follower, which is 17 millimeters. Like that. Into that, then just draw a faint circle like that. This may not be outlined, it's sufficient like that. Right, then the direction it's anti-clockwise, standing at the center, then in between the space between the camshaft, like that. All right, that would show the direction. It's anti-clockwise, so it's moving in a different direction. Right. We are also given this information, right, from the tip end to that, it's 8 millimeters. Then we have got 53 millimeters, and the thickness of this one is 8. Okay, let's start with the 8 millimeters. Remember, in all this, speed is critical. Okay, right? So then you measure 53. Mark that. Right, you also measure 4. 4 millimeters and 4 millimeters like that. Let's just check. Take this one down. Like that. Just erase this. My T-square moved. You want to be as accurate as possible. Right, let me redraw this. That's 4. And my other 4 will be here. Okay. There you go. It's 60 degrees. 60 degrees. You can outline this now. There you go. So this is the given information. We have got the camshaft, we have got the follower, right, which is a wedge-shaped follower, which is also regarded as a point follower. It can also be referred to as a needle-shaped follower, right? It's one and the same thing, okay? Right, so it's wedge, it's point, it's needle, okay? Which would refer to one and the same thing. Right, so now we have got this follower. We are told that it descends 56 millimeters with uniform acceleration and retardation over the first 180 degrees. We shall consider that. It rises 20 millimeters with uniform motion over the next 45 degrees. There is a dwell period for the next 45 degrees. Right, remember when we are talking about the dwell, it means the follower is neither rising nor falling, okay? Right, the other term which can be used in place of dwell is resting, it's stationary. So it can be said to be stationary. It does not mean that the cam is not rotating. It basically means that it is not rising, it is not falling. It returns to its original position with simple harmonic motion over the rest of the rotation. So you'd find that we have got this, right? It would rise all the way, right, with uniform acceleration and retardation. Then it rises, it falls initially, right? Remember, when it is on the other side, right, if it is drawn here, right, we normally refer to the movement away from the camshaft as rising and the movement towards the camshaft as falling. But in this case, the examiner described this movement going downwards as falling, which is descending, right, and the movement towards the camshaft as rising, okay? So I don't want you to get confused with what we discussed earlier on, right? It's situational, it's in context, okay? Right, so the instructions are as follows. Draw to scale 1:1 the given camshaft and the wedge-shaped follower at the minimum distance. Right, the minimum distance, that's the distance from here to there. That's what we've done. Draw to a rotational scale 30 degrees is equal to 8 millimeters and a displacement scale of 1:1. The complete displacement graph for the required motion. Label the displacement graph and include the scale. Project and draw the cam profile from the displacement graph. Show the direction of rotation on the cam profile. Show all construction and projection. So some of the things, like I said, these should be routine. The moment you have got the camshaft diameter, draw that camshaft, outline the camshaft as a diameter and etch it. Right, the moment you are given the minimum distance, show that minimum distance, the space in between the camshaft and the minimum distance, that's what you have to define as for the direction of rotation. So we have got the camshaft, we have got the direction, we have got the minimum, then already, if we are dealing with the wedge-shaped follower, we started right at the minimum distance like that. But remember, if you are dealing with the roller follower, right, you would find that you may need to find the center of the roller, then you draw the roller, then you measure the displacement, okay? Right, from what we have gathered here, right, the total displacement would be 56. That is moving from here to there, that's 56. Right, because the rise or the falling is 56, then it begins to rise up until it comes back there. So let's measure 56. You measure 56. Which is here. Right, once you have measured that, you now draw the maximum diameter, which is basically the description of the extent of either falling or rising to give you the displacement. Right, so you are going to draw a faint circle like this. Right. Once you have defined that faint circle, you can even divide it into 12 equal parts. There you go. Right, so we have got everything now divided into, in terms of the circle, it's divided into 12 equal parts. This is our point 0, right, which would also be equal to 360 degrees. Right, since we are moving in an anti-clockwise direction, this should be our 30 degrees, 30, 60, and 90, right, 290, which would give you 180, right? That's 120, 150, and 180. Then 270, which is that one, 300 and 330. Right, we can also define the center line now that we have got this information. Define the center line. Right. There you go. Right, so that's a center line, and this is also a center line, okay? Then at this point, you can also now draw the extent of the displacement graph, the space in between from here to there, that's our 56, which is our total displacement. That can also be referred to as the maximum displacement, the stroke. Let's create the starting position. But maybe before we do create that starting position, we want to find the extent of our length of the displacement graph. We are given this information that 30 degrees is equal to 8 millimeters. Right, therefore 360 degrees is equal to, right, proportionally 360 will be more, so 360 degrees over 30 degrees multiplied by 8 millimeters, right, over 1. We should be able to get, right, if we calculate this, let's take our calculator. (360) divided by 30 multiplied by 8 would get 96 millimeters, okay? Right, that is the length of our displacement graph. So we come with that 96, we measure, just to check where you will be able to get 96. but without interfering so much. If I mark here and there, right? Project this one up, and this one too. Right. So the distance from here to there, that's 96, which is the same as that one. You can make this one slightly darker than a construction line, but not as dark as an outline, right? Just to make sure that you are able to define your graph properly. There you go. Okay. And the other thing, we can divide this one into 12 equal parts. Divide this one into 12 equal parts. And use the actual 1 millimeter interval, 10 millimeter intervals like this. So it's just like as good as 1, 2, 3, up to 12. Right, we connect this one to them. Right, we know that we could measure from here to there. That's 8, 8, 8, but they are marks which are awarded for showing those divisions. Right, you come here. Right, then you take these ones down. Right, okay. Right, since we are starting from the bottom, right, we can as well number, right, we are starting from here, that would be our point 0 in terms of degrees. Right, it says the first 180, so from here, that's 30, 60, 90, 120, 150, 180, then we write 180 there. Then it rises, right after falling, like that, then it goes back, that's rising, 20 millimeters with uniform motion over the next 45 degrees, right? So this is 30, we don't have 45. So what we do is you take your 45 degrees set square, you miter there, and you also miter there, like that. One, you simply measure 4 millimeters, then you get that. Okay. Right. So if we are moving from here, that's 210 plus 15, that's 220. and 25. So we have got 225 there, right? These are degrees. Then there is a dwell for a period, dwell period for 45 degrees, right? That's 15, that's 15 plus 30, that's 45 degrees. We have got here up to this point, we have got there, that's 210, that's 240, that's 270. So we indicate like that. Then we are left with 1, 2, 3 divisions, okay? These would take us to 360 degrees. So 0 to 180, that's uniform acceleration and retardation. Right, then from 180 to 225, right, there is a rise with the uniform velocity. Then from 225 to 270, there is a dwell. Then from 270 to 360, there is movement with the simple harmonic motion. Right, so we now want to look at this. Remember, when it is uniform acceleration and retardation, the first thing that you need to do, you count 1, 2, 3, 4, 5, 6. There are 6 divisions, right? So you also require 6 divisions this side. But you just draw a line. Even if it interferes with the circle, it's fine. These are constructions, right? Then you can actually use the normal 6 divisions. Right, you have got number 1, 2, 3, 4, 5, and 6. Okay, but this is connected here. Like that. Take a set square and a straight edge, align to the end line, and you slide. There you go. Right, so you have got 1, 2, 3, 4, 5, 6 divisions, okay? Technically, these divisions, right, would say this is the same as, right, that's 30, right, that's 60, 90 degrees, 120, 150, and 180 degrees. Right, so from here, that's 30, 60, 90, 120, 150, and 180. Such that if you look at this 180 and a 180, there's a point that you are supposed to locate here. All right. Now, remember what we talked about. If it is uniform acceleration and retardation, all right, from start to finish, you can just connect with a straight line like that. There should be a line like that in terms of your construction. Right. Then you count 1, 2, 3 to halfway point. Remember, it's 4, 5, and 6, so 3. Right. You project these lines to the halfway line. That's 1, 2, and 3. You do the same here. Right. If you do this, you'll find that you would get to 1 and the same point. All right. Then you have got this. You've got that. So depending on when you are starting, would you say from these points 1, 2 up to there, that's our first half. Then 1, 2, and 3. That's our second half. So for uniform acceleration and retardation, right, remember this is 30 degrees, this is 60 degrees, this is 90, 120, 150, and 180. So for the first half, right, you want a 30 and a 30 to connect somewhere like that. So the connection point is here, but 30 degrees and this one like that. Then you do the same for 60 degrees like that. But 60 and 60, they would meet here. That's the point that we want. Then for 90, and it's already there. Then we are done with the first half. Then we go to the second half. You connect on the other side or from the other side like that. This is 120, right? This is 120, so the meeting point is here. Connect like that. This is 150 and this is 150. The meeting point is there. Then you connect with free hands like this. There you go. Right. If you are satisfied, then you can outline this. There you go. Okay. Right. So that is our graph, right? Which is starting from point 0 up until to point 180 degrees. Right. So as this follower is moving away from the shaft, it would take this, or it would define this graph on the plotter, okay? Right, relative to how it is making contact with the cam itself. So the graph would be a description like that. Then once we have done that, from this point now, it says it rises 20 millimeters with uniform motion over the next 45 degrees. From here to there, that's 30. From here to there, that's 15. So altogether from here to there, that's 45. So you go to the 45 millimeter, to the 45 degree point, which is actually 225. You measure from there 20 millimeters. You connected this because it's uniform velocity like that. You have got that, okay, which is up to this point. Then it says there's a dwell period for the next 45 degrees. From here to there, that's 50. From here to there, that's 30. Altogether, that would give you 45, okay? Now, if you are certain, you can as well outline this as well. There you go. Right, so we have got this graph all the way up to there, then it begins to rise, right? Then it dwells, it is not rising, it is not falling. Then the last leg, it says it returns to its original position with simple harmonic motion over the rest of the diagram. We have got three, remember, with simple harmonic motion, that's why we make use of a semicircle. All right, the number of divisions, and in it they should be even. The number of divisions from here to there is 3. So you can also draw a semicircle and divide it into 3 equal parts. That is over 180, that could be 60, 120, and 180. So 3 divisions would suffice. But if you want to be more accurate with regards to your graph, right? You can subdivide these ones into 15 degrees, 15 degrees, 15 degrees, 15 degrees, such that if you divide this one into 6 equal parts, there would also be 6 equal parts here. So let's do that so that we have got a much clearer and well-defined graph. So you might have there as well, like that. Turn it around. There you go. Then you can also project this one and find the center. Remember, everything that you would want to do in drawing, show that you have got a different understanding. But I'll take this one all the way since we shall require it later on. Right, stand here. Open to there and check. So open to this side. Let's draw a semicircle like that. There you go. Right. You divide this semicircle into the same number of divisions from here to there. Remember, this is now 15, 30, 45, 60, right, 75, and 90, which is 30, 60, and 90. So the size in terms of the divisions would not change anything. Right, we divide this one. Right. There you go. Right. Now, we know that at this point, this is 270, which is also 270 here, right? 270 plus 15, we are talking about 285, right? 285 plus 15, just a moment. 270 plus 15, that's 285 plus 15, right? That's 300. So here we have got 300. Then we have got 315. We have got 330. We have got 345. Right. So what it means also here, we've got 285, right? 300, 315, 330, 345, and 360. Right, so the same number of divisions which are here should be the same also this side. So what you need to do now, right? 270 and 270 is already there. Then you have got that. That's 285. Right, that's 300. That's 300, then 315. $330 and 345, like that. You have got this point, you have got that point, this point, that point, that point, and that point. Right, you connect these points nicely. Right, like that. Then if you are satisfied, you define this one now. By way of an outline. Okay, so from here to there, remember what I said, you could divide this one into 3 divisions. That's 1, 2, and 3, also in line with these divisions. So this one was going to be here, and the next one was going to be there, and the last one. But in terms of loci, you want as many points as possible, such that you are able to draw a cleaner and clearer graph in terms of the curve. Let me just try to redraw this one like that, and do the same this side. Like that. Right. Blue, it seems it's more clearer than the red one. There you go. So that's our displacement graph. The next thing that we want to do now is to do the labels. Right. We have got here, that's our displacement graph. We can also indicate the scale and the type of rotation, right? This side, that's the vertical displacement. Right, so we can write it, displacement in millimeters. The first thing here, displacement graph, right? Then you write also rotation in degrees. Then you define the scale, which is 30 degrees is equal to 8 millimeters. So the distance from here to there, it's 8 millimeters, 8, 8, 8. But remember, you need this construction in order to get all the full marks. Right, once you have the displacement graph, right, you can now project from the points on the curve with regards to the displacement graph to the line of action, then projected in terms of the swing with the camber standing here, right to the relevant point. Let's start with 30 degrees, right? This is 30, right? We take it there. Then we go to 60, right? We have got 90 to the line of action, 120, 150, then 180 is already there, right? The first part, right? That's about 30 degrees, which is here. Then you swing it like that through to 30 degrees, right? Opposing the direction, right? Then you go to 60 degrees, which is here, right? That's 60. Then you also swing it like that, right? You go there. Then you go to 90 right, which is here, and you swing it like this, and 120, which is here, right? Then you also swing it like that. And then from there, that's 150. Adjust properly, right? You also swing it like that. That's 150. 180 is already there. Right, okay. Then you can connect these points. That's a point, that's a point, that's a point, another one, and another one up to there. Right, nicely. The initial construction should be very faint. You can make a mistake, that's fine. Back to there. Right, so that's the initial. Right, but if you are satisfied, right, you can then outline this. Like that. There you go. Okay. Right. So that's your first part from here to there, which defines the rise. Okay. In this case, which is the 4, is this thing is falling downward like that. So the movement is going down and up, going down and up. Okay. Right. Then we now want to look at the movement from here to there. But you do the same thing, right? This is 120, like that. At 210, right? From here to there. Then from there, you have got 225. Right. So what you would require, right? We know that from 180 to 210, that's fine, but this has been subdivided between 210 and 240. Right, so you come here, you bisect this. There's an upper line like that. Stand on the other side. Cut this as well as that. Okay. Or you can simply use a 45-degree set square. This, and you draw a line like that. You also take note of this. This is 220, 225 degrees. All right, okay. Right. So from here up to this, right, you are going to rise, right? Then there's a dwell from 225. Let's first of all define that. That's 210. Right, like this. That's 225. Right, so from this point to that point and that point, you need a connection. You do it from the outer side, like that. right? Then we know that there's a dwell from here to 270, from this point to 270, right? There's a dwell, right? Whenever there is a dwell, you are not going to do much. You simply outline from here. Like that. Using a canvas, like that. There you go. Let me also outline this part. Like that. So that is the movement. That's 210, that's 225. Then from there, there's a dwell. A dwell is not rising, it's not falling, right? It is maintaining the same height, right? Okay. We also now have got spaces in between for 285, right? We do the same thing. I set, stand here. Set like that. Right, we do the same. Do the same. The division. Remember, you can also do this with the canvas, with the set square, right? But I want to show the principles of construction so that you will see the link between grade 10 work and grade 12 in terms of constructions, right? Okay. So we can say this is 285, that's 300. The other one is 315, that's 330, that's 345. This one is 300, like that. I'm just showing you so that you are aware of what we are doing. Right. So if I project this one, which is 285, take that so that we don't get confused. Stand on the camshaft center and you describe like that to 285. That's a point, right? Then you also need 300. Project this to the line of action. Stand there. That's 300. All right, then we have got 315. But it's already there. Let's describe that. So that's 315. All right, then we have got 330. That we project from here to the line of action. Which is here. But last but not least, that is 345, which is here. Stand there. Project project like that. Then we have got this point. We have got that point, we have got that point, we have got that point, we have got that point. All these points can now be connected. You do it from the outside. Like that. If we are satisfied, you can outline this. Right, remember it has to be a smooth curve. There you go. Right. That is our chem profile or our chem disk. You can even come here and outline this right nicely. Chem disk or the chem profile. Right. So from the information that you were given, right, you needed to redraw that. You also needed to define the direction of rotation, the minimum diameter, the maximum diameter, show the center lines, then from there come up with the displacement graph according to the motion, all right? Remember, where you have got fractions in terms of divisions, these linear divisions, you can just miter with the 45 degrees set square like that, you get half, or you can measure from here to there. If it is 8 millimeters from here to there, you measure 4 millimeters like that. Those divisions are critical, and sometimes they may also want you to show, right, that you are dealing with different lines for those particular additional divisions. Okay, just something like this. Like that. Then you also come here. Right, okay. They are the normal divisions which are here, but they are these additional, okay? Just to show them with a different line, right? So that anyone would look at your work would be able to tell, oh, right, they are these additional. What are they for and what are they representing? Now, when you have done this, you would have completed your work, okay? Right, show all construction and projections, the projections we did, the constructions we did, and the labels we were able to define all that. Now, this has now taken us to the end of this topic on chems, right? So next time when we meet, we are now going to look at a new topic, but still under the umbrella term Loci, but we are going to look at mechanisms. I hope you enjoyed this lesson as much as I did, and I wish to see you again tomorrow as we embark on a new topic with regards to Loci. Thank you. Enjoy the rest of your evening. Good night.